Okay, so this video, what we're looking at here is kind of basically coming straight off the energy and fuels video, just looking particularly at combustion of fuels and energy changes that are occurring in fuels. Okay. So what we're going to do is we're going to start with the concept of combustion of fuels. And we're going to break that off into complete combustion, and then we're going to out of that incomplete. Okay. Now, generally, in all of our questions and our problems, we evidently assume complete combustion is occurring. Okay, and complete combustion occurs when we have a very light blue or a almost clear flame. So I'm just going to put that there, blue flame. And what we are getting here is we're getting complete products forming of CO2 gas and H2O gas generally as well. Okay, so we assume that we can perform our calculations really easily based upon the concept of complete combustion. On the other hand, though, if you think what's happening and occurring from a real life application perspective, incomplete combustion occurs a lot of the time. Okay, an incomplete combustion, we're running an experiment in using our Bunsen flames. We do visually see complete combustion occurring when we have that orange flame. Okay, and it's a much cooler flame, so it's burned to the temperature it's burning is to a lesser extent. And the reason it's burning to a lesser extent is because we've restricted the amount of oxygen able to be able to get into the combustion reactor, into the Bunsen burner. Okay, so we're limiting oxygen. So rather than oxygen being in excess, it's a limiting reagent. And if oxygen's a limiting reagent, we can't completely form CO2 and H2O. Get oxygen, form carbon dioxide and H2O, or you can actually get carbon and H2O. And we particularly see that second option, the carbon and H2O form. We've seen that in our combustion reactions when we've used the can to heat up water to work out our enthalpy values, and we see that black kind of soot, that black carbon effectively form on the bottom of the can. And we're seeing that byproduct is present in that reaction rather than reforming CO2. If we have incomplete combustion, we're burning our fuel to a lesser extent, and therefore our enthalpy change would be lower than if we were looking at complete combustion. So the two processes cannot be well compared to one another. They are effectively completely different reactions. Okay, so what I want to take us to now is we're going to assume complete combustion, as I said before, and we're going to look at energy changes. Okay, and we'll look at the two types of energy changes, but we'll hone in on the major one in regards to fuels. Okay, so every type of reaction can be classified as either two types based upon the energy changes occurring. A reaction can either be endothermic or it can be exothermic. So the classification of each depends on the amount of chemical energy in the products. Sorry, I'll say in the reactants versus the amount of chemical energy in the products. Okay, so we show that, and we demonstrate this using an energy profile diagram. Okay, so your Q value of energy is on the y-axis, and then the x-axis is in time. We'll start with a certain amount of energy of your product, at whatever X energy. For our reaction to go ahead, we must input energy into our system. right? And that is our activation energy because we need to break the intramolecular bonds within the products. Okay, we have to break apart our products. Okay. Once we reach that activation energy threshold, our reaction takes place. We reform new products at a particular energy level. What I've drawn here is a typical endothermic um, energy profile diagram. All right. Our energy changes, well, the concept of energy change is actually given under the term enthalpy. Okay, enthalpy means the amount of chemical energy present. Okay, we use the symbol H to demonstrate. So I'm going to write here on my energy profile diagram the H of my products is here, and now I've got the H, oh sorry, that was meant to be reactants, and the H of my products. Okay, according to my graph, I can clearly see the H, the energy of my products is greater than the energy that I had in my reactants. If I have more energy in my product, that energy had to have come from somewhere. Okay, so therefore, energy is absorbed. The energy is absorbed from the surrounds. What then that categorizes as what we as humans visually observe this as is we see this as a cooling or a decrease in temperature. Okay, because if we were performing an endothermic reaction, the reaction's taking place. The energy has to come from somewhere. Now, if we're testing the temperature as we go, the energy is coming from the surround. So therefore, as we're testing the temperature, the thermometer is going to show that the energy in the surrounds is decreasing because it's moving into reforming the energy of the products. All right. So a great example of this, of an endothermic reaction, is those cool, what do you call them? Like the snap packs. If you play footy or something like that, you would have seen them where you snap them and they go cold instantaneously. So what you're doing with that is you're breaking the two compartments in these like what do you call ice packs is the word I'm looking for. And when you break them, when you snap the ice pack, you're allowing two chemicals to mix. These two chemicals react in an endothermic reaction. And endothermically, they therefore absorb the energy from the atmosphere. And if they're absorbing the energy into the chemical bond, we're basically removing heat energy from the system surrounding the reaction. And so that they are very, very cold to touch. Okay. We'll add on to our diagram here that this amount of energy from our initial point of energy, heat of reactants, to the highest point of our graph is our activation energy. Okay, the energy required to break the intramolecular forces of the reactants. There will always be an activation energy, okay, of any reaction. Some of activation energies are very small and some of them are much, much greater, and it will depend on the reactants in the system and the situation that we're dealing with, but there will always be an activation energy. Okay, if we're looking therefore at delta H value of our change in energy, will always be the energy of our products minus the energy of our reactants, and therefore our value will always be a positive value for an endothermic reaction. Okay, so let's take all those same concepts and look at energy over time. We'll have a particular amount of energy of our reactants. We'll have a certain amount of energy to break the intramolecular forces. Those molecular forces are broken, the reactant particles are broken into atoms, think about it that way, and the reforming products of an exothermic reaction, less chemical energy. The energy of the products is less than that of the reactants. So we've got energy of our reactant, energy of our product. This is still Okay. What this means, what this difference means here is that we have a heat discrepancy or an energy discrepancy. We've got a difference in energy. We've got too much energy in a sense. And what we know that means is that energy is released, or we get an expulsion of energy into the environment surrounding the reaction. Okay, so H is less than energy of reactants. Therefore, energy is released. Excess energy is released, and we generally see that in heat. Okay, our dot KK, a change in energy, our change, the heat of our energy, our test minus the energy of our reaction. The same process to work that out, but because we're looking at a smaller value of our energy of our products than our reactants, we know our value will be negative in every time. All right, so enthalpy value, whenever you're showing an enthalpy value, you're asked to show change in energy, enthalpy value must show the sign. Okay, and a lot of you in the last few assessments have missed that component, so you must show the negative value, and we're generally then going to show that in kilojoules per mole. Okay, so the second part of this video is looking at gases. Okay, linking all this in, you probably remember the major component of all of this work is just calculations. Calculations, working out enthalpy values, using specific heat values, calculating the amount of reactant, how of fuel required, and so on. All of that sort of stuff we'll probably go through, particularly when we get back into class, but it's just lots and lots of calculation practice. But I'll just remind you in terms of gases, what we talked about a little bit is that concept of pressure, that concept of gas pressure, and what that means is talking about the force exerted in a given volume. Okay, force exerted in a given volume. All right, generally we measure pressure in kilopascals or in atmospheres. And remember that you might have to convert between different units, and those conversions are found in the data book. I think it's 1 atmosphere to 101.3 kilopascals or something very similar to that. When we think about gases, we think about the three as a okay. We think about volume, and we think about temperature. Each of these different factors of a gas affects one another. So if we increase the temperature of a gas, what we're also going to do therefore is increase the pressure, the partial pressure of that gas on the container, because we're increasing the amount of kinetic energy available. If we decrease the volume, okay, so let's say if we have a syringe full of gas and we try and we put our finger over the end and we decrease the volume, what that also is going to do is increase the amount of pressure, because we're increasing the amount of particles per given volume. All right, so you have a concept, have an idea, a general idea of what each of these determinants are in terms of how we describe the behavior of a gas. Okay, we don't need to look at some of the Boyle's law and a few of these other laws around the influence of pressure and volume and temperature, but just have an idea and a good understanding of the behavior of a gas and what happens if you increase or decrease pressure or volume or temperature. We know pressure, we need to get pressure in our calculations. Our volume is in liters, Kelvin, which is 200. You have been given the value in. What that allows us to do is it allows us to calculate how much we have. And how we do that is we use our ideal gas formula. Now remember, an ideal gas does not exist. What we're doing is we have to consider basically, we have to remove the fluctuations that occurred due to elastic collisions and other behavioral aspects of a gas. So we're removing those instances because the mathematics would be a lot harder, and we're replacing that with this formula, the ideal gas formula. So we use pressure, we use volume. Pressure and volume will equal the amount in mole times R, which you remember is a constant of 8.31, times your temperature in Kelvin. And we can manipulate this equation to work out any of those values. If we need to work out moles, we can work out moles, that temperature, and so on. All right. But what this has allowed us to remember, hopefully, is this was our final piece of the puzzle for calculating the amount of something. Okay, so if we have, I'll do it down here. If we have a fuel and we're reacting with oxygen, produce CO2, whoops, to produce CO2 and H2O, what we can now do is if we have the mole of this fuel here, we can therefore determine the amount of mole of CO2 that would be produced using our stoichiometry. Okay, we can use that value. We've also able to use a little bit of a cheat version of that, considering a concept called molar volume. So the molar volume is a laboratory, it's something that you'd use only in the lab because we have to be at standard lab conditions. And basically what it says, or what it's been determined, considering an ideal gas, is that if you have 1 mole of any gas, any ideal gas, that gas will be at 22.4 litres at standard lab conditions, which is 1 atmosphere and 24 degrees Celsius. I can't remember the exact conditions. But it allows us to use that comparative. All right. So therefore, if we had 2 moles of gas, we would double our volume and we would have 44.8 litres. Okay. So we can use our formula, which is also in the data book. Molar volume equals volume over total volume over the amount of gas in the mole. All right. And you can manipulate that equation. If you have a gas at standard lab conditions, you know that the molar volume is 22.4 per 1 mole. If you have, like I said, if you have 10 moles, we're going to be multiplying that volume, that molar volume value by 10 to work out what actual value the gas takes up. There's just one more thing I will actually go through. Just get a new slide up. And that's kind of just remembering how to link all this sort of stuff, everything we've talked about, and link it all together. All right, I'm going to just write a chemical equation, methane. Okay, we've got 2 of those, and 2 of those. And we'll have a delta H equals a negative value. Right. So remember this, what I've written here, I've written a thermochemical equation. It's a thermochemical equation because I'm showing the enthalpy value. So anytime you're asked to show a thermochemical equation, we have to show what the enthalpy value is. We have to include that in our overall equation. All right, and that value is really important. So I'm going to. Okay, so I've just looked up the value for methane is 890. So I'm actually. So from our reaction here, we can see that for 1 mole, put that in here, 1 mole of methane, we will produce 890 kilojoules. And remember, it's our fuel which links to this value here. All right, that's what's really important. All right, and let's just take this value. This is an energy value. Oh, sorry, it's an alpha H value that is determined by the amount of energy per mole of fuel. And that is a really, really important formula. And when we started this work, a lot of you got stuck when you weren't sure what the next couple of steps were if you were calculating a question. And what's really important to remember is your enthalpy value tells you something really, really important. Okay, so I'm just gonna do a little quick example. All right, my example is going to be, considering this whole scenario, methane is burnt and the energy released is 2,000 kilojoules. Okay. All right, so you've been told the energy released is 2,000 kilojoules, and my question is, how much CH4 was combusted or was burnt, whatever way you want to say it. Okay, so what we've got here is we've got a few pieces of information. You've been told here that you've got 2,000 kilojoules of energy that has been released. All right, but what's really important in piece of information is this piece of information, it tells us another important relationship. It's telling us that if we have 1 mole, we release 890 kilojoules. So if we've released 2,000 kilojoules, think about it. Well, we've obviously got more than 1 mole, but we need to work it out actually correctly mathematically. Okay, so we have a Q value that is 2,000. We have a delta H value, theoretically, where your fuel releases 890 per 1 mole, so 890. What we're looking for is, the mole. That's our question, which is what I've asked you for. So rearranging this formula, the mole of CH4 equal the Q value divided by the delta H value. So your Q value, your 2,000, divided by 890, and we get a mole value of 2.25 moles of methane reacting. Okay, 2.25 moles of this, answering our question. What we can then do from that point onwards is what we have the ability to do is then for now we have a mole value. So what we can do is we can work out, well, theoretically, how many mole of oxygen do I need? Well, I'm going to need at least double that because I've got 2 moles of oxygen reacting. I need at least that amount to ensure that oxygen's reacting in excess, preferably more. What also I can do is jump to my product, and I can work out how many mole of CO2 according to my stoichiometry and how many mole of H2O as well if needed to work out, well, okay, how many mole of greenhouse gases are being produced or how many mole of CO2 is being produced for that 2,000 kilojoules. Okay, just really important that when you have an enthalpy value, if you are asked, well, how many mole of CO2 are produced per given 2,000 kilojoules, we can't just jump straight to CO2. We have to go, okay, I know my enthalpy is given in 890 kilojoules per my mole of fuel. So I work out, okay, well, how many mole of fuel delivered this much energy? And then I use my stoichiometry back that way. Okay, if you're a little bit rusty on this sort of work, this was a topic that I videoed in our first remote learning. So the stream videos, you can go and have a look at some of those, but it's just lots and lots of chemical questions, lots and lots of practice. Start simple and then just get harder and harder from there on. All right, well, that's it for today.